When you look at a tree, its age is usually the first thing that pops into your head. How old is that big oak? 100, 200 years? But if you really want to know more about that tree's life, you have to do a little math. And no, I don't mean multiplying its age by 100 to get the number of rings. I mean counting the rings themselves, specifically the patterns within those rings. And because tree rings provide a high-resolution, year-by-year record of Earth's environmental history, they remain one of the most precise tools available for reconstructing past climates. See, each ring is made up of two different colored layers. There's the light stuff which forms in the spring when the tree starts growing again after winter, and the dark stuff which forms in late summer or fall when the weather starts to cool. Together, these layers form one annual ring, and if you count them up, you'll know how old the tree is. But tree rings can tell us more than just the age of the tree. They can also tell us about the conditions that the tree was growing in, which is the whole premise behind dendrochronology, the scientific study of tree rings. Basically, you can use them to reconstruct past climates going back thousands of years. Here's how it works. Take a look at this cross-section of a tree. You can see that some of the rings are wider than others. That's because some years the growing conditions were just better, warmer temperatures, more rainfall. The tree had all the ingredients it needed to grow big and grow fast. So it laid down a wide ring that year. But sometimes the conditions weren't so great, maybe a drought, cold spells, or other environmental stresses. So the tree grew less that year and its ring is narrower. What's really cool is that by looking at a bunch of trees in the same area, you can match up their ring patterns. Like here, you can see that the wide ring from 1969 and the narrow ring from 1970 are the same in all three trees. This happens because trees in the same environment are responding to the same conditions. And by overlapping their rings, you can make a continuous climate record going back as far as the oldest tree in your sample. And it doesn't even have to be living trees. Dead trees, stumps, and even archaeological timber can be used to reconstruct past climates. We can also use other features in the rings to learn more about past environments. For example, trees can take up more carbon in years with higher carbon dioxide levels. So by measuring the carbon in each ring, we can see how the amount changed over time. There are also chemicals that accumulate in the rings when the tree is exposed to things like sulfur dioxide, which can come from volcanoes or burning fossil fuels. And that's not all. By studying the isotopes or different forms of elements like oxygen and hydrogen in the rings, we can learn even more about past climates and the processes happening in the water cycle. Dendrochronology has helped scientists understand long-term climate variations, date historical structures and artifacts, and validate other climate data sources like ice cores and sediment layers.